Bill, can you hear me?
Yes, I can. Yes, I can.
Perfect. Could you turn on your camera, please?
Turn on my camera.
Yeah, that's perfect. Could we get a
Okay.
picture of Bill here, please?
Yeah.
Oh, perfect. Good morning.
Yep. Here in the breakfast room.
What did you have for breakfast?
Just a few pieces of fruit and a cup of coffee.
Okay. I think that will carry you through the lecture, I hope.
I think so.
So what's the weather in Berkeley?
Oh, well, it's beautiful fall weather. Crystal blue sky, about 55 degrees
Wow.
Fahrenheit. You know,
Yeah.
chilly and cool, but just perfect.
Yeah.
Yeah, this is one part of the country where, apart from forest fires anyway, you really can't beat the weather.
You have snow.
Well, snow is about 3 hours away up in the Sierra Nevada.
I know. I have snow in our garden.
Hello,
I'm
Martin.
sure. It sounds like Martin Quack.
Yes, it is indeed.
Yes. Can you see me, or Bill?
No.
I see you, Martin. You look great.
Yeah. You know the house, right?
Morning, Bill.
Yeah.
Good morning.
Well, of course, I've been in this house 50 years now, so you've been here.
So, if the rest of you guys could leave Bill alone now, and we could start to see if you could share your screen.
Okay.
We'll remove my picture. Yes. So, welcome to the third session for today. At this session, we will have 2 presentations. The first one will be by Bill Miller, and the second one will be by Nancy Makri. So let's see how it's going for Bill here. If you can get up and share the screen, please.
Okay, let's see.
Hey, you're close to Silicon Valley. The computers, of course, work in a different way there, right?
Sometimes, that's right. Let's see what goes here now.
Here we go, yes.
Yep.
Right, I remember seeing that. Could you go over in full screen mode, please?
Okay, let's see. Okay, now where is full screen?
Yeah, he's going down.
Bottom left, bottom right.
No, not that.
Bottom right, you have a little icon. There you are.
There we go.
Perfect, Bill. So you will have 40 minutes from now. So about 6:35 Central European time, I will show up and you will know I want you to wrap it up. How is that?
Okay, yeah. Tell me when to quit, because I could go on a lot longer.
I bet. So you better start now. So the webinar is yours.
Okay. Well, thank you very much. And it's great being in Uppsala again, even if only virtually. And my first thing, I just want to congratulate Nancy Makri and Tom Miller for being the Löwdin lecturers. We were fortunate to have them at Berkeley for some of their early years. Nancy as a grad student and Tom as a postdoc. But the things they've been doing in recent years has just been outstanding and incredible. And I'm going to talk about some of my work a little later, but you'll see it is so simple-minded compared to what Nancy and Tom have been able to do. So I think you'll really you'll see that in a few minutes. Nancy after me, and then Tom tomorrow. But before getting started, I wanted to mention something about my interactions with Per Löwdin. My first time I ever met him was after my first year as a graduate student. My friend Frank Weinhold and I talked the chemistry department into letting us come to the summer school in summer of '64. It was 1 week in Uppsala and then another week in Abisko, way up north of the Arctic Circle. And of course, Per was just a force of nature. I mean, the sessions would go on all day and then until 10 o'clock in the evening. And finally we would, and so forth. It was my first time in Europe. I bought a VW in Germany and drove around Germany a week or so. And in fact, I at the time I remember thinking, I said, boy, this is great. I really want to be a postdoc here one day when I finish up and get the chance. And unfortunately I did. Anyway, so, and I learned a lot about projection operators in the summer school, and which has been useful through my whole career. Then the next time was during my third year as a grad student. I talked my research director, Bright Wilson, into letting me go to the Sanibel Symposium that was actually on Sanibel Island. And that was interesting. I had begun in my graduate work working. Bright Wilson had suggested I work on this problem on lower bounds for eigenvalues. So I started on that and came up with some new tricks for that. And Per was interested in lower bounds at that time. So we had some very energetic and lively discussions. And Per was, he was very supportive. I mean, even though in some sense we were competitors, although I was a grad student, how could I compete with him? But anyway, he was very supportive, and I really enjoyed it. It was really great. And then, of course, many other Sanibel symposia at different parts in Florida. In my mother's last year, she lived with my sister in Gainesville. So every year I took the opportunity to go to the Sanibel Symposium so I could visit there. So that was really a great experience. So, okay, let me tell you about some of the work. This probably maybe be the last creative scientific work I do, you never know. But this work is all with my last postdoc, Steve Cotton, who left just last year. So these are the papers. If you're interested in any of this, you can look it up and find the papers, mostly in JChemPhys, but in some other places too. So the motivation was to look at some, well, the idea in dealing with complex molecular systems, we all want to do quantum dynamics. That's the right answer. But it's just not feasible for, in systems with hundreds and hundreds of atoms and so forth. The one thing that everybody does is classical molecular dynamics. In my early part of my career in the early 70s, we developed some semi-classical ways of using classical mechanics within a semi-classical framework. And in the later 70s, when Dieter Meyer was a postdoc with me, we really wanted to generalize these early semi-classical methods to deal with electronically non-adiabatic dynamics. Well, for a semi-classical theory, you first need the classical mechanics, and then you can feed the classical mechanics into the semi-classical apparatus and come out in a well-defined way. But how do you deal with, what's the classical mechanics when you have, say, a number of electronic states that are coupled with the nuclear degrees of freedom? Well, the only consistent thing, then there are many ways to go about it. There are a lot of so-called mixed quantum classical approaches where the idea is, well, you certainly got to treat the electrons quantum mechanically, and we want to treat the nuclei classically, since we have many nuclear degrees of freedom. Then we need to mix these two some way. Well, there are a lot of things you can do in that framework, and a lot of people have done that. But our attitude in the late 70s was, if we really wanted a dynamically consistent theory, the only thing really to do is, if we're going to treat the nuclei classically, was to treat also the electronic degrees of freedom classically. But how do you do that? So that's the first step in this work. And this is an old idea. I'm going to go through it kind of quickly, but some of you may know about this. The idea was, this was Dieter and I came up, this is kind of our heuristic derivation of this approach, is to say, okay, suppose we, we start with a diabatic electronic mechanics. We aren't trying to do quantum chemistry. We're assuming that we or other people can do the quantum chemistry. We come up with a diabatic electronic matrix that depends parametrically on nuclear coordinates in the normal way. And for the moment, suppose the nuclei follow some trajectory, capital R of T, then this would be the time-dependent Schrodinger equation for the electronic amplitudes for these various electronic states K, say N of them. Now, these amplitudes are complex if you write them in this terms of a magnitude and a phase this way, and then express the electronic energy, namely just the expectation value of the electronic matrix with these amplitudes. This is then the electronic energy as a function of the N and Q. And we think of N and Q as a pair of classical action angle variables. So this is a classical electronic Hamiltonian in our point of view in terms of these generalized coordinates and momenta, these action angle variables. Then if we take this as the classical Hamiltonian, then Hamilton's equations, standard Q dots, DH, DN, and so forth, we show that it's elementary arithmetic to show that this pair of first order linear differential equations is equivalent to this one complex first order differential equation for the amplitudes. So just doing the classical mechanics with these degrees of freedom is really equivalent to solving the time-dependent Schrodinger equation. So we think of this as the classical electronic Hamiltonian as a function of nuclear coordinates. And then we add in nuclear kinetic energy. So this is now the full classical vibronic Hamiltonian in terms of the nuclear coordinates and momenta, and then these electronic generalized coordinates and momenta. And then we can just compute Hamilton's equations classically for all the degrees of freedom, integrating all the degrees of freedom simultaneously classically. So that's the primitive idea. Now there's in the early days, we really didn't do the calculations in action angle variables because, as you see, it involves sines and cosines, and computer programs were a lot slower if you had sines and cosines in those days. Nobody understands that now, but some of you old timers do. So we actually made a canonical transformation from these action angle variables. This is just classical mechanics again, to these Cartesian-like variables of P, N, and X for each electronic state. And this is that same Hamiltonian, exactly the same Hamiltonian, just with this change of variable. And now you see explicitly that each electronic state is now characterized as a harmonic oscillator. And the occupation, the action variables are really the semi-classically become the quantum numbers for these electronic harmonic oscillators. And then there's the off-diagonal part. So you can see now why this is potentially practical. If this idea really works, and we have 1,000 nuclear degrees of freedom and 2 or 3 electronic states, now we have a classical Hamiltonian with just 1,002 or 1,003 classical degrees of freedom. We just added one vibrational mode, if you like. So the electronics degrees of freedom really just appear like vibrations. Now there's a different way. Now Gerhard Stock and Mike had been a postdoc with me that followed Dieter, and then Michael Toss was one of his graduate students back in Germany. When Stock got back, he and Toss came up with a different way of approaching the problem, and that actually is more straightforward. You just write down the quantum mechanical Hamiltonian operator in terms of nuclear coordinate and momentum operators. And then this is the diabatic electronic matrix. And these are creation annihilation operators that create and destroy population in electronic states. Here, I'm calling them I and J rather than K and K prime, but the same thing. And this is an exact vibronic Hamiltonian operator. Then if one chooses, now you don't have to do this. There are other ways to do it. But if you do choose the underlying degrees of freedom of the creation annihilation operators to be boson. This is known as Schwinger bosonization as bosons. Now, bosonic symmetry doesn't enter into anything that in the case, so they're mainly just harmonic oscillators. Then we know the creation annihilation operators for harmonic oscillator are just the raising and lowering operators expressed this way in terms of the Cartesian oscillator coordinates and momenta. And then if we replace A and A dagger in this form, we see that this is the Hamiltonian. You can see it's exactly the Hamiltonian that Dieter and I came up with in a very heuristic way. So the Hamiltonian is straightforward, and it's an exact Hamiltonian if we made everything an operator. But of course, we're going to go to the other limit where we make them everything classical. So classically, it's an exact Hamiltonian operator. Now, the next step in the model is how does one get electronic state information? How do you get electronic transition probabilities from this? Well, again, as I said, the electronic degrees of freedom are just like vibrations. So think, how did do it in the old days? How did you get vibrational state-to-state information? Well, there is an exact classical prescription for that came out from some of our early semi-classical work. Namely, it's just a Jacobian value. You find trajectories that go from one integer value. Semi-classically, the vibrational states are integers of the classical vibrational action variable. So you find trajectories that go from one integer value for the initial state to a particular final value for the final state. We did some of that in the old days. That's not practical to do. It's a nonlinear boundary value problem, and that's a very tricky thing to really implement, certainly with many degrees of freedom. Therefore, you really make, and actually what you make some practical progress by and actually works better too. If you take this classical expression and average it over the final quantum number by a little bit, say plus minus gamma, and gamma was initially always a half. Well, if you do this averaging process of this Jacobian factor, you see this is exactly what you need. If you do this sloppy calculus, cancel out the dn2s, dq1 comes upstairs. This then becomes an integral over the initial angle variable over its range 0 to 2 pi. And then you have to put in a little Heaviside function that picks out the range of the angles for which the final final action variable is within plus minus gamma about the integer value for that quantum state for that of the oscillator. So and then typically this integral is done by Monte Carlo. Well, this is the old quasi-classical model. This was used before we derived it this way. It was used when I was a beginning graduate student. Martin Karplus and other people were using this to do vibrational state-to-state transitions in simple atom, usually in just simple atom-diatom collision processes. Well, this is not great, but it works pretty well. One of the problems with it is not microscopically reversible because you begin with an integer action for the initial state, but then you accept final actions within a little window about that integer value. Well, we pointed out in the late 70s that you could actually make this microscopically reversible if you also averaged over the initial action variable by a little plus minus gamma about its initial integer value. So we think of these, we now refer to these as little window functions. And now you see this as a phase space average. If h bar were not 1, this would be 2 pi h bar. And we know phase space averages are invariant to when you do them. You can integrate, you can do the phase space average over the initial values or over the phase space values of the final values and integrate backwards. The integrand is the same. And so this is manifestly microscopically reversible. Well, so anyway, this is the way we quantize in this primitive way these vibrational degrees of freedom when we want state information. Now, it's interesting to compare this with what quantum mechanics would do. If we're doing our vibronic transition quantum mechanically, we would begin with the initial electron nuclear wave function for the initial electronic state, propagate it with the propagator. And then if we wanted the probability at any time t later of being in a particular final state, we would just project out that final state from this time evolving electron nuclear wave function. And there are no hops. It's totally continuous time evolution. If you want the probability at a later time, you just keep you just keep propagating this. So you know what? You don't restart it. You just keep propagating as long as you can. And at any time along that you want to know the probability of being in a particular state, you just interrogate it by this projection process. Well, if you write this down, this here, and then then its complex conjugate. Then you see this is the projection operator, a la Löwdin, onto the final electronic state, Heisenberg time evolved. And if you take this kit and bring it around with this bra, that's the projection operator at time 0 on the initial electronic state. So you see the time-dependent transition probability is just a time correlation function, like so many things in dynamics. You can usually express anything that you're interested in as a time correlation function. And you see, that's exactly the form of this classical expression. You replace the trace by a phase space average, which is this typical classical limit of a trace. These projection operators have now become these little window functions. And you see, each final, another thing, each final state has its own ensemble of trajectories. So one trajectory doesn't contribute it only contributes to the final state for the trajectory that lies in that window. Okay, so that's the primitive way that we quantize these vibrational gradients. Well, this is a little pedagogical example. The first thing I suggested, Steve, I said, Steve, we tried this old symmetrical quasi-classical thing back in the late 70s. It gave terrible results. And so these are the results. So this is the old standard problem, collinear H plus H2. It was in the 60s, that was the benchmark that everyone wanted to get right. So this is looking at the ground state H plus H2 reaction probability as a function of energy. And the points are the quantum results, which of course not trivial to generate on your iPhone probably. The red curve was the result of Martin Karplas's unsymmetrical quasi-classical model. That actually people still use that, you see it's not great, but it's qualitatively correct. It shows a threshold, no tunneling, of course, in it, and it rises from threshold. Well, when we tried our old symmetrical quasi-classical, doing windowing of the initial and the final vibrational states with this window parameter of a half, we got the green curve. Well, you see, that's really terrible. I thought it would be good because it would smear out this classical threshold, and it does smear it out by much too much. So now the next motivation came from some work by really in the 90s by Lauren Bonnet, using this old-fashioned unsymmetrical quasi-classical model for a lot of small polyatomic chemical reactions to quantize vibrational states. And he found out he got better results when he had benchmarks to compare with. If he took the windows, he used Gaussian windows. And actually, Steve tried Gaussian windows too. Gaussian windows, and we found for our cases that the histograms and the Gaussians gave very, very similar results. The crucial thing was that you shrunk them down. Instead of them being the full integer width, in this case, if you shrunk them down to be about only half an integer width, plus minus a quarter, that gave the blue curve. So, and that does agree much more satisfactorily with the quantum results than obviously taking them to be a full integer width, which is what we had done. We never thought about shrinking them down in the old days. And I might just point out, if you took these window functions to be Wigner functions for these vibrational states, which is another possibility, and actually if you do that, you get something called the classical Wigner model, which comes out of a linearized approximation to semi-classical theory. But if you do that using Wigner functions, you get terrible results in this case for it. Sometimes they work quite well, but in this case, for example, you for the ground state it smears out the result, but it smears it out much too much because these window functions as a function of the action variable is really an exponential in the action rather than just a narrow histogram about the integer action. Okay, so of course I told Steve nobody cares anything about H plus H2, but if this symmetrical quasi-classical model were to work for quantizing these electronic oscillators in this old Miller-Hamiltonian, then that might really be interesting. So let's just see how far we can get with such a simple primitive model. So the first test case we did for the non-electronically non-adiabatic problem was a couple of these little toy models that John Tully had used, and a lot of people have used these to test out some of their various approaches. So one on the model, so there's just a one-dimensional scattering problem, and these are the two diabatic potential curves. And there's a single curve crossing. So that's the simplest thing. And Landau-Zener, of course, would just do this perfectly well. Then a little more interesting is when the two diabatic potentials cross in two places. So semi-classically, you have the possibility of crossing at one avoided crossing region and another possibility of crossing at the other. And the transition probability is the square of an S matrix, just the sum of the amplitudes of crossing at one or crossing at two. And we understand that extremely well for many, many years, many decades, that how Landau-Zener-Stuckelberg describes those so-called Stuckelberg oscillations appropriately. Well, here we do the, let me skip this. This is a choice of what do we use for gamma. I won't go through this, but it's just a parameter for how narrow you take the window functions. There are some good reasons. If you take it to be 0, that's when the window function squeeze down to delta functions. That's too narrow. Gamma of a half is the maximum value because otherwise the windows overlap, and that's not appropriate. There are good reasons. I won't go through this argument for a gamma that has this particular value around 0.366. So and actually Steve had found empirically that values of gamma around 0.3 and 0.4 really seem to be giving him the best results. So I told him just see if you can find any parameter range for which we get sensible results. So this is with our Goldilocks gamma. 0.36, and this is the single curve crossing compared to the quantum results, and you see it really works quite well. This is the double curve crossing problem. Now this is interesting because these Stuckelberg, these are quantum coherence effects to come about semi-classically from adding amplitudes and squaring. But here we're getting those out of strictly just the classical molecular dynamics, this idiot-proof classical MD. And that surprised a lot of people. I won't take time to explain. You can think about it. Why are we getting quantum coherence, which we are, with this totally classical molecular dynamics of treatment? Well, so then we said, gee, these are trivial problems. One of the popular models of complex systems has been the spin boson model. I know probably many of you know about this. Two electronic states. Whoops. It's a telephone call. These spin boson models, two electronic states, the diabatic potentials, the nuclear potentials are harmonic oscillators, but with many, many harmonic modes. We typically take 200 or 300 modes. And then the frequencies of the oscillators, there's a distribution of frequencies, usually chosen from some analytic functional form. In this case, the so-called ohmic distribution, where it's linear in omega with an exponential cutoff. And and then various parameters, strong coupling, weak coupling, et cetera, and so forth. So Steve, these calculations are easy to do. The classical MD is trivial, of course. And fully quantum calculations can also be done for these using this hierarchy equations of motion method and others. Nancy Makri did some of their earliest fully accurate quantum calculations, these spin boson models. And you see, the agreement with the quantum results of the dots, and these are they're not here. Here you can see that the classical results are dephasing a little bit too fast. We understand, if I get time to explain why we think that's happening. It's a quantum effect in the nuclear degrees of freedom. The high frequency nuclear vibrational modes tend to get frozen out and be only in the ground. So whereas classically, they can be populated classically and add to decoy. So it decoheres a little too fast. Okay, this is the asymmetric spin boson. So these are plotting really its population differences between the two initial states that start out in one state, and this is the difference of that from the other. And you can see in this case the difference goes to zero at long time, and the degenerate when the two harmonic wells have the same energy. Here they just go to their detail balance ratio. There's a question about, and then Steve has done literally many dozens of these many different parameters. There's in the weak couple, when the electronic coupling to the nuclei is weak. Remember these two electronic states are just two harmonic oscillators. The quantum values of the oscillators are 1, 0 and 0, 1. You begin in one of these and the excitation hops back and forth. Ultimately, that gets thermalized by coupling to the nuclear bath. But if the coupling is weak, it may hop back and forth a number of times before it gets thermalized. And that is the so-called quantum coherence regime. If the coupling is really strong, you begin in one of the, say 1, 0, the excitation hops and it gets thermalized before it ever has a chance to hop back. That's the incoherent regime. Okay, many examples. There's a lot of discussion about detail balance. Simple, anyway, I don't have time to go through this, but detail balance, it's described quite well. It doesn't have detail balance problems. That's Ehrenfest treatment. Ehrenfest gives terrible results for detail balance. The symmetrical quasi-classical model, at least for this little example that John Tully used, gives the detail balance result exactly. It's not always exact for real systems, but for these little model problems. Let me go on. There's a lot of, to make the models, these models a little more into the site exciton models are a little more realistic model of a complex system. So if you have two states, in a molecular system where the excitation is on one site or another site, those are the two electronic states, but on each site, the nuclear environment is different than it is when the excitation is on the other site. So this is a model where each electronic state has its own nuclear bath that's different. And this can be used, and actually is used, to model real molecular systems where you can do some, you have the excitation on one site, do a classical molecular dynamics for just that one electronic state on that site, and and then Fourier transform the force correlation function, and then get a realistic treatment of the harmonic, of the vibrational environment around that site and then around the other site. And so here we have two states, now we have two baths and et cetera. And so again, there are many parameters, examples of these models. HEOM is a hierarchy equations of motion method. These calculations were done by Ishisaki, who was a postdoc with Graham Fleming at the time, as a model for this FMO photoreaction center site. And again, weak coupling regime, strong coupling regimes. You see, this primitive quasi-classical business has worked better than I ever thought it would work. I mean, there's no reason that it has to work this well. And in many different regimes. This is a case of four sites, each site having its own bath of say 300 vibrational bath modes. So this is some thousand or more nuclear degrees of freedom of these different harmonic sites, and again, comparing to the HEOM results, again, these HEOM can only really be done in these very special model systems. But so even though they're limited, they are very useful. And like I said, Nancy Makri has done some using her methodology, has done some of these. This is four electronic states. This is showing, I don't have time to explain this either, but not only do we get the populations, which are really the diagonal elements of the electronic density matrix, This same quasi-symmetrical quasi-classical model can give one the off-diagonal electronic density matrix. These are the various off-diagonal electronic density matrix for this four-state system. Again, comparing the black lines are HEOM results, the colored lines are the symmetrical quasi-classical business. And again, it just it's amazing to me that it has worked so well. 5 electronic states, 24 electronic states. Steve got carried away and showed he could actually do with 96 electronic, et cetera. So let me talk maybe just a few minutes, talk about the electronic, what I've talked about models, and most of these model problems are defined in a diabatic representation. But many times, one, especially with ab initio results, one will be generating the adiabatic potential surfaces and their couplings. So there is an adiabatic version of this Meyer, actually in the original paper with Dieter Meyer, we worked out the adiabatic version of that classical electronic vibronic Hamiltonian. You just have to diagonalize these oscillators, and you do that by diagonalizing the diabatic matrix. And the eigenvalues are the Born-Oppenheimer surfaces, potential surfaces. And when you carry out the classical canonical transformation, it's all just classical mechanics, you get a correction to the nuclear momentum. It's really a vector potential, exactly the kind of vector potential in electromagnetic radiation theory. But it's in this case, and here it is, it's proportional to the derivative coupling that we know from many non-adiabatic treatments. And these are the electronic variables that go along with that. Again, this is an exact Hamiltonian quantum mechanically if you made all the standard quantum mechanical operators. Here, of course, we treat them all classically. So it's an exact classic. It's exactly the same Hamiltonian with just a change of representation. Now, when you write out Hamilton's equations for this, it's all straightforward to write it down. The complicating feature in using it is that the time derivative of the nuclear momentum involves the derivative with respect to r. And there's the derivative of this, of course, which is just the normal forces from the adiabatic surfaces. But the delta p, this vector potential term, also depends on r. So you have to differentiate it with respect to r, and that leads to the second derivative. So this is just like in quantum mechanics, and it arrives for exactly the same reasons as it does quantum mechanically. So you need not only the first derivative coupling, but you need the second derivative coupling. And well, that just raises the complication of implementing this. And then most of the times the second derivative coupling gets neglected. But Steve pointed out that if you work with this quantity called the kinematic momentum, namely the P plus delta P, then you see that P plus delta, so the R dot is just P kinematic divided by the mass. But we need an expression for the time derivative of the kinematic momentum. Well, you just write it down and differentiate it as P dot. We know we had said P dot before, involves the Born-Oppenheimer part and the second derivative coupling. But we also have to differentiate this with respect to time, delta P. And when you do that, you get these two terms. You just use the chain rule. You get these two terms, but we know what x dot and little x and little p dot are. And then this second derivative coupling term exactly cancels the second derivative coupling here. So the time derivative of P kinematic involves only the first derivative coupling, and there's no approximation. It's exactly equivalent. Now, the equations of motion, we were in terms of using P kinematic, they're not Hamilton's equations anymore, but they are exactly equivalent to Hamilton's equations. So we just integrate those. And these are just some examples. This will be the last thing I'm sure I have any time to talk about. We did the calculations first for some of our old spin boson models. And so there are 4 calculations here. One is the original calculation in the original diabatic representation. that is essentially exact for our purposes. Then there's the calculation using the adiabatic representation, including the first and second derivative coupling. It gives exactly the same results. And then the calculation using these modified equations in terms of peak kinematic, that also gives exactly the same results. So those three calculations are numerically identical. The fourth is when we use the canonical equations, but neglect the second derivative coupling. And you see with this set of parameters, and that's the red curve, that's the one, that's the only one of the three curves that's different, four curves that's different. It doesn't make much difference. But when we make delta is really the H12, it's the electronic, the non-adiabatic electronic coupling. But when we make that 10 times smaller, then you only need 10th, so make the coupling much narrower. Then when we neglect the second derivative coupling, that's the other three curves are still identical. But when we neglect the second derivative coupling in the canonical equations, it can make an enormous amount of error. And the reason is clear. When H12 is large, when you go by an avoided crossing, the derivative coupling has a peak, but it's kind of broad. It's a broad peak. And the second derivative coupling, which is basically the derivative of this, is then much smaller. But when H12 is really small, the avoided crossing is very sharp. And the first derivative coupling is much more delta function-like. And then the second derivative coupling is even larger. So that would be exactly the case if you were coming close to a conical intersection. Conical intersections are actually exact crossings, and no trajectory ever goes exactly through a conical intersection. They just become more or less close to it. And when it comes close to a canonical intersection, that's like passing through a very sharply avoided crossing, etc. So I have my feeling that my time is up, and
That's right.
so I'll stop. As you see, there were eight or 10 papers. Steve was very prolific. He's a great writer. He was a lawyer until he decided to come back to graduate school. Anyway, so you can read them anyway. Thanks.
So thank you very much, Bill. This was very interesting.
You're going to see Nancy and Tom are going to do things so much more sophisticated than this, that this is kind of laughable.
Well,
but
this was
fun.
pretty sophisticated to me. It's almost like I feel I should ask Nancy to ask the questions. But I have one sort of conceptual question. Why did you choose classical dynamics to describe a quantum phenomena? What was the driving force behind that? Was it because alternative explanations, or because it's faster and simpler?
Well, it is faster and simpler. That's probably the main reason. But also the reason was that we thought if we're going to you can never make a mixed quantum classical treatment dynamically consistent. You've got to make some assumptions. Well, that's okay. We all make assumptions. But we thought it would be better to be consistent in treating the nuclear and electronic degrees of freedom in exactly the same framework classically, and actually, we've used this old Meyer-Miller business. We've actually used it in semi-classical theory, which is more sophisticated, more difficult to implement, but is also more accurate. But we decided the goal with Steve was just how far can we go with these really primitive kind of treatments, because this is something that anybody, of course, I say anybody can do them. They can do them provided they have the potential energy surfaces. And for real systems, that's still the bottleneck always. But that's not going to go away. But to the extent that you can do the quantum chemistry to get the potential surfaces, then doing the dynamics of a complex system. Nowadays, people doing protein dynamics and all these things that all you guys do now. Most people are totally happy if they could it's hard enough just to do the classical MD to get the potential surfaces. Yeah. And it's not going to be perfect, but I used to always tell my friends, that's the nice thing about doing kinetics. We're not looking for 8 significant figures. We're looking for 2 significant figures if we're lucky.
I have a question from the audience here that was posted down in the Q&A. It's a question from Asmus. And he says, thank you for a very interesting talk. You mentioned that you had more arguments for why the classical trajectory decoherence faster than their quantum mechanical equivalents for your spin boson results. Could you go a bit more into detail as to why? And do you also see this for other systems?
Yes, this is one example. Yeah, so this is the case. This is the third state side exciton model. One of the things it did. This is the case where this is one of the most discrepancies that we've seen in these. That this is the case. So there's 7 states starting in the red state. So the decay here from the quasi-classical model compared to the quantum results is too fast, and it decoheres a little too fast. You have to go about 15% longer in time before this is falling. Well, the reason our understanding of the reason is that, and this is at 77 degrees Kelvin. So at low temperature, the high frequencies of the nuclear bath are really frozen out, and they don't cause any decoherence anymore. They just kind of shift the potential curves a little bit. And actually, and you can see that that's partially correct. When we go to 300 degrees Kelvin for this same problem, you can see the agreement is much better. And that's because these high frequency modes that are frozen out don't contribute to the decoherence. And so, but classically they do. Even at low temperature, a classical oscillator still can vibrate a little bit in the bottom of it. So whereas quantum mechanically, it can't. It's frozen into the ground vibrational state. So that's so as I said, we think of this as there are nuclear quantum effects. And actually, Nancy and Tom, the things they do can deal also with nuclear quantum effects. I'm pretty sure they're going to tell us about that. So we just decided, okay, there are nuclear quantum effects. We just won't worry about those. There are nuclear quantum effects even with just one potential surface, no electronic states. And people, if they can do those for complex systems, usually they're quite happy to be able to do them. So we decided we would, give up that last level of really precision and be happy if we could just do as well as plain old quantum, just plain old classical MD, including electronic degrees of freedom, as well as we can do for the nuclear degrees of freedom. And we won't get nuclear tunneling effects, but we will get quantum coherence effects in the electronic degrees of freedom. That, as I said, I could explain that more, but I probably don't want to take too much Nancy's time.
So yes, thank you very much for that reply. Thank you very much for your presentation. So now we move on towards the last presentation, which is by Nancy. Can you hear me, Nancy?
Yes.
Oh, fine. How are you doing today?
Good. How are you?
Congratulations, Nancy. Congratulations.
Thank you.
So hello. How are you doing?
Very good. Thanks.
So you should have been here asking Bill the questions rather than me. I think you would have done a much better work. And by the way, congratulations to the honorary title of being the Löwdin Lecturer of 2019.
Thank you very much.
We're so proud having you here, and we really look forward to listen to your presentation. So if you could kindly share your screen with us, I will let you off. I think most people would like to listen to you and then head off for something else. So let's not keep them waiting. This looks interesting. Yeah. So the webinar is yours.
Thank you very much. I would like to thank Roland and the other organizers for the opportunity for putting together this wonderful virtual workshop, and the opportunity. It's a tremendous honor for me and a great pleasure to be participating in this celebration of the legacy of Per Olof Löwdin. Even though I did not get to interact with Löwdin, I certainly have used several of his tools. I teach some of his methods and have used them in research, definitely. So I I am going to talk about quantum dynamics, and fortunately, some of the previous speakers already introduced quantum dynamics. It's a very interesting subject, very exciting to be able to probe the dynamics of chemical processes. So just to set the stage here, what we want to do is observe the dynamics of a quantum mechanical system
Vi
in
startar
some
4
large
minuter sent
environment.
va, ungefär va? Okej, bra.
Excuse me?
Sorry.
Okay. So we would like to follow the dynamics of a quantum system in a large environment, condensed phase, or biological environment. And we would like to probe that system and not probe the rest of the environment. So what we do is propagate the initial density operator to time t, and then trace out all the degrees of freedom that we are not observing directly. This gives us a reduced density matrix. So this is a standard quantum mechanics problem. We could solve this. We could propagate this by propagating wave functions of the states that are in the initial density operator, and we solve this time-dependent Schrödinger equation. In principle, we can do this. But in practice, when we have systems with many electronic states and even more vibrational states and nuclei moving around, and a real complex system, the volume of Hilbert space is huge. And wave function methods don't scale very well in that case. They're not very practical. So what we're going to do is take a different approach. And we're going to follow the path integral formulation. So this is actually a very nice formulation. I think conceptually, it's basically the double slit experiment generalized. So you have a quantum mechanical amplitude for getting from here to there in some time t, and the amplitude is the sum of amplitudes along all possible paths the system can follow. So you get this expression here. The quantity that you are summing in the amplitude is a phase that has the classical action in the exponent. So you make the connection with classical mechanics really very transparent. Can be used for quantum statistical mechanics as well, imaginary time, and really has all the beautiful features of quantum mechanics. This is exact quantum mechanics. It's not an approximation. So in practice, of course, what you would like to do is evaluate this. And if you can do this, you could get away with wave functions. You would not have to worry about the practical inability to store wave functions. To store wave functions from the number of degrees of freedom is huge. So can we do this? Well, the number of paths here is infinite in principle. Of course, in practice, what you always do is discretize things. So we can discretize a time into a time step, and we're going to discretize the spatial coordinate or coordinates, and here it is. And if I have n grid points along my spatial coordinates, and if I just quickly count how many paths I get that connect the initial point and last point, I get n to the power of t over delta t, the number of time steps that I'm propagating over. So we don't have wave functions, but we have exponential growth of the number of paths with time, and that's a problem because very quickly the number of paths grows too large to enumerate. You cannot really sum them. You get huge exponents. Even with a two-state system, if I want to go to 100 time steps, I get 2 to the 100th power paths. That's too many. At the same time, stochastic methods, Monte Carlo methods, don't really work here because the integrand is highly oscillatory. It has a modulus of 1. It's the same everywhere in weight. And we get enormous cancellation. And of course, this cancellation is important. All of quantum interference is in this cancellation, constructive or destructive interference. But you can't really sample this in an inexpensive way just by using Monte Carlo. So what can we do? So here's the idea. I'm going to give an analogy here. What we'd like to do is find some way to maybe disentangle this sum without approximation. We're trying to do rigorous calculations without approximations or assumptions. And give an analogy here. Let's say I want to do this multiplication. So at a glance, you look at it, and I've got to do 3 long multiplications to get this result. But if I look at it more carefully, I recognize that there are 25s hidden in here, and there are 4s hidden in the other factors. And if I combine the factors separately, I get 25 times 4, that's 100, and there are 200s here. So in the end, all I need to do is single-digit multiplication and add zeros. I'm done. exact, no approximation. So this is basically the idea and what we try to do. What we would like to do is analyze the structure of the path integral and exploit the physics of the process to arrive at the decompositions of the path integral, exact decompositions that allow us to calculate the sum over all the paths without approximations. And I'm going to tell you about some success stories. We had success in this regard in doing this in 3 different situations over the years. I'm going to tell you quickly about all of these. The first of these, just skip some slides here. What's happening? There we go. This first of these is the old case of system bath dynamics. Now, Bill talked about it a little bit, about spin boson, Hamiltonians, and so on. It's a system, a small system coupled to a large bath of harmonic oscillators. That's the system bath Hamiltonian. And back a long time ago, back in the 90s, we developed the first viable methodology, path integral methodology, for dealing with the dynamics of system bath Hamiltonians with linear scaling with propagation time. Now, this is something really old. And I've talked about this a long time ago, and then I stopped talking about this because it was really old. But now we have some very recent developments that are very exciting. So I'm going to tell you a little bit about this. So as I said, this has been applied to a lot of calculations, spin boson dynamics, reaction rates, spectra, laser control, and so on, a lot of things. So how does this work? So if I take a system coupled to a harmonic bath and I express the density operator at time t, the propagator, in terms of the system components and the propagators for the environment, the harmonic oscillators. Harmonic oscillators are Gaussian functions in the propagator, and one can integrate them out analytically. This is all Feynman's work, of course, a long time ago. And what you get is this influence functional that modifies the amplitude of the quantum system alone. All the effects of the environment are here. But the moment you go to this subspace, here you only have the system paths. The moment you go to the subspace, what you pay a price, that you now get non-local correlations, get non-local interactions in time, and all of your path integral variables are coupled together. This is actually something that happens in classical mechanics as well. This gives rise to the kernel in the generalized Langevin equation. But what we realized back then was that these couplings, interactions, don't go on forever. Memory doesn't last forever, it's finite. So all you have to do is write down the paths within the memory length of your system. And then what you do is you can iterate this array of paths, and you arrive at the tensor decomposition of the path integral in this case. That's back in the 90s. And since we have an iterative procedure, we have linear scaling with propagation time. So this method has been used a lot. As I said, it can be used with any spectral density, no assumptions here. And everything is beautiful if you're doing small systems, except that we have to store those tensors. And as long as you can store the tensor of this many elements, n is the number of states or points or sites of my system, and delta k max is the length of memory in units of the time step. As long as you can store this tensor, everything is fine. But if the memory is very long, or if you have multi-state systems, then you can't really converge this easily. There are various tricks to enhance convergence, and we're going to talk about them. But I would like to tell you about a very recent development here that I'm very excited about. This is 2020 work. In fact, the last of these papers just published online yesterday. So it turns out that even though all the path integral variables, here we go, all the path integral variables within the memory length are coupled together, they're entangled, you can disentangle them in an iterative way, recursive way, can start decomposing this and shifting the entanglement term to longer time separations. And when you do this, you make those entanglement terms smaller and smaller as you go along. And the result of this is an expression, and this is an exact decomposition, analytical expression, analytical decomposition. it's you can decompose the reduced density matrix into a series of small matrix multiplications. These involve small matrices, n squared by n squared matrices of system size, no tensors, no need for storage or tensors. So this is really, I think it's interesting theoretically, and with this parameter here, R max, that is what we call the entanglement length. And I think it is interesting theoretically, but also very important practically in practice, because there are situations like this. Here's a two-state system, but in a regime, in a really very difficult regime of very, very long memory. Here, now we can go to memory length of 100 units. We've gone to 200 units, and we can converge the dynamics. And finally, we get a population of two-level system to go to symmetric two-level system to go to 0.50, okay, exactly where it should go. Because if you can converge this, you don't get the right long time lived here. And so we can tackle very long memory, but we can also treat large systems. Here's an 11-state system. This is exact quantum mechanics, a 16-state system. We can do multi-state system, and I think it's going to become a great tool to use. And just to tell you about the kinds of, we always like to do some real systems and some analytical investigations. Just to mention what we are doing lately in this regard, there's a lot of interest in decoherence, studying decoherence and quantifying decoherence. And one of the measures that has been used to quantify decoherence is purity, the purity of the reduced density matrix. That's the trace of the square of the reduced density matrix. And if I have a pure state, then that's equal to 1, stays equal to 1, but we don't have a pure state here. So what does this do? And the general assumption and discussion in the literature is that this purity decays monotonically, and it looks like this. Here's a population, here's the purity. If you assume it's like this, and you look at it at very short times and examine the short time dynamics, you can get a sense for how long decoherence is in the system. Well, that is not necessarily the case, though. And what we're finding is that when you have low coupling in between system and environment and low temperature, what you get is the purity starts to go down, but quickly goes back up and follows an interesting pattern and kind of saturates, it settles at some really high value. It's almost a pure state here, not quite, but almost. So this actually easy to understand in the end, and it's a complex interplay among an incoherent evolution and in the instantaneous rate. It turns out the rate of the oscillations, the faster they are, the faster the greater the effect they have on increasing purity, and also the population difference they all push the purity back up. And you can have situations like this, where you would think that the purity goes down, but in fact it does not. And you can relate this to what the decoherence is in this system. Now, in case people think that this is just a fictitious idea of a peculiar model, this is actually very real. And if we look at the dynamics, I'm going to talk about the chlorophyll dimer dynamics later. But here, let me just show you what the purity does in this case. So here's the chlorophyll dimer, and we're looking at the excitation energy transfer and the purity of that process. And here's exactly what it does. It does something like this. Here's the purity. It goes back up quickly. This is at room temperature and stabilizes like this, does not decay very much. So let me move on to my second subject, and this is something that is closely related to what Bill talked about, the quantum classical path integral. So we're trying to do quantum classical dynamics. Here we have a system in a complex environment, not a harmonic path, in general, a complex environment, a solvent, biological molecule, and we would like to do, Bill referred to this as consistent dynamics, consistent quantum classical dynamics. Of course, if you're using wave functions, you can't do this. You run into the Ehrenfest dilemma because the quantum system is delocalized, the wave function is delocalized. Where do you evaluate the force that leads to that dilemma? And Bill has a very elegant way of doing this by mapping the quantum discrete Hamiltonian into a continuous one. Then you have a one unique continuous Hamiltonian that we can treat by classical mechanics. If we want to stick to the quantum representation of a system, though, can you have consistent quantum classical dynamics? Can you go beyond approximations that make assumptions here? And the answer is yes, and the path-integral formulation offers a unique advantage in this regard, because unlike wave functions, quantum paths in the path integral are local, just like trajectories. So if you adopt a path integral representation of the system, you no longer have to evaluate averages, like in the Ehrenfest force. So we derived this, we formulated some years ago the quantum classical path integral, which it's a rigorous derivation, comes down to the following. For the quantum degrees of freedom, you sum over all the paths. For the classical degrees of freedom, you include only the classical trajectories. And each of these path trajectory combinations carries a phase, a unique phase, and the phase carries all the details of the interaction between system and environment. So QCPI is the rigorous quantum classical limit. In fact, it becomes exact if the environment is harmonic bath. It uses classical trajectories for the environment and treats all the interaction in full detail, no averaging whatsoever. And it accounts for all the decoherence precisely, automatically through phase cancellation. Everything is there. We don't have to insert any additional factors or anything. Now, each path in the QCPI formulation, each path of the system defines a sequence of forces that drive the classical trajectory of the solvent. So I get as many classical trajectories from a given initial condition as there are quantum paths. But the number of quantum paths grows exponentially. Paths proliferate exponentially, so do trajectories in this formulation. So it looks like it's not easy to evaluate at all. And what we have done is to analyze the physics of the process and exploit it to be able to arrive at a computationally feasible scheme. So one of the main ingredients in this scheme is that out of the astronomical number of trajectories that you get from each initial condition in the QCPI formulation, you can take a single one of them, can be this one, can be the one stays in the donor state, could be something else, even better, but a single trajectory actually can give you all the, through fluctuations of the energy levels, and I think my video is not playing here, or is it playing today? The fluctuation of the energy levels that you get, all right, it's not playing. The fluctuation of the energy levels give rise to dephasing, and you can show that this accounts for energy transfer between system and environment through the absorption and stimulated emission of phonons. It's actually something that is very similar to the interaction of a molecule with light in the classical treatment. So a single trajectory can include most of this is what I call classical decoherence, can include all this classical decoherence, which is most of the decoherence. So we can get ahead by incorporating this in our zero Fourier propagators. And what is left, the rest that's left, of course, is very important. What is left is what we call quantum decoherence. This includes all the processes having to do with a back reaction. The system pushes back on the bath, on the environment. There are all these different paths here, and they all have phases. And these phases are important. They're very delicate, but very important because they give us the tail balance. But exploiting the interplay of these two in good ways, in appropriate ways, we're able to very much accelerate QCPI, and we can make it a viable method that is practical for condensed phase calculations. Something else that you need to do is in quantum classical calculations, this is something that applies to more generally, not just to QCPI. Often you need to quantize initial conditions. That means you need to come up with a phase-based distribution that is quantized, includes quantum effects. And this is not an easy task at all. And several others here have developed methods for quantizing the Wigner distribution. I would like to mention a very simple method we have developed that is based on classical adiabatic switching, as well as a path integral method that involves starts with the coherent state representation that has some advantages. And these are useful for quantizing the density in quantum classical, quantize the density for use in quantum classical calculations, or even in just classical calculations, just pure molecular dynamics. And here is an application that illustrates QCPI. This is an electron transfer reaction in solution where we treated 1,300 solvent atoms interacting with a charm force field. By this method, full QCPI, full quantum classical calculation, everything is taken into account here in great detail. And what you see here is a snapshot of a calculation. I mentioned all these different trajectories whose phases are important, and it is through superposition of those phases that we get quantum effects. So what you see here is 3 snapshots. Well, one snapshot where we are superposing 3 different trajectories. You see the atoms have landed at a different place along these 3 different trajectories, and it is the interference of these phases that that gives you all these quantum effects and coherence as well as decoherence. And it looks like we get delocalization here of atoms that are classical atoms. These are atoms treated by classical mechanics, and yet we're seeing quantum delocalization because of this quantum superposition. And we can converge the populations, and there are interesting things here I'm not going to tell you about because I need to move on. We've done proton transfer. We've looked at proton transfer reactions as well in model solvents, as well as protonated water dimers and trimers in biological channels. And we're seeing some subtle quantum effects here in addition to the classical effects in these processes. And let me move to the third situation, third case, which is a case of extended systems. So third case where we can do an exact decomposition, we're back to exact quantum mechanics, no quantum classical, an exact decomposition of a path integral that gives us linear scaling with system length, system size. And in addition, we're able to include all intramolecular vibrations, harmonic normal mode vibrations, at essentially no cost. So these are the kinds of systems that we targeting with MPI. And let me tell you how this works. So here I have, let's say, a chain, an array of units that I call A, B, C, D, and so on. And this can be very long. Each of these can be molecular units, could have electronic states as well as vibrations. So in a molecular aggregate, typically what I have is 2 electronic states here, ground and excited state in each of these units. So if I have n units, the dimension of the Hilbert space is 2 to the nth. This is not, so I'm going to show you some examples in a moment on quantum Ising models. This is when we use 20, if we use, say, 20 units in a calculation, this is not 20 states, it's 2 to the 20 states. So just the electronic Hilbert space here is huge. Now, in addition to this, we've got vibrations. There could be 100 molecular vibrations in each of these units. And if 3 of these are occupied, of the states are occupied on average at a given temperature, then you get an enormous Hilbert space of the vibrational Hamiltonians. And the way MPI works is actually, in the end, very simple in a sense. We write down all the paths, the quantum paths for each of these units, and we connect them. And it comes down to the end to something like putting together a puzzle or building something out of Legos. These are the building blocks. This is time, these are time steps, and these are the monomer, the units, the monomer number, unit 1, 2, 3, and so on like this, or A, B, C, and so on like this. And we just bring in those building blocks one at a time. And we can go to any length because we have linear scaling with a number of units in the system. So here's an example. Quantum Ising chains, or the more general form of these, the Heisenberg Hamiltonian. And in these systems, again, the Hilbert space is the full number of states of all the units. So for 20 units, Hilbert space of the spin states is 2 to the 20th. Now, in addition, what you see here in these curves are results that we get when we couple vibrations. We couple phonon baths to each of these units, in each of these spins. They represent the local environment of those spins. And what you get is enormous complexity here in these dynamics, and in the something you couldn't really do at all if you had to enumerate all the states. thermally average them. And we're looking at interesting behaviors. There are really interesting behaviors here, and there are interesting phase diagrams. We're trying to map out those phase diagrams because we're trying to look at the coherent incoherent transition and quantum phase transitions in these systems, and they're very interesting effects. But let me tell you how we do this, how we include vibrations and phonons. So here's an example, and I'm now using the form of excitation energy transfer and exciton, Frankel exciton Hamiltonian. Here, this would be the Hamiltonian for the electronic states. They're coupled between units, between those molecular units. And each of these electronic states, the ground and the excited state, have their own vibrational degrees of freedom coupled to them. So these are normal mode vibrations, for instance, even though we could go beyond that as well. We are going to go beyond that very soon. So now what we have is each of our units, it's like a spin boson. It's like a system bath system. And we know how to treat that. We know how to do system bath dynamics for each of the units. So now we do MPI to couple those units together, and we're able to include all the vibrations and go to very long systems with linear scaling. So we have been very interested lately in studying excitation energy transfer. And this is one of my favorite systems. I've been interested in these systems for a long time. So we have with aggregates of biological molecules, chlorophylls. And they play a very important role in photosynthesis, for instance. And there are big questions, there are interesting open questions about quantum coherence and the efficiency of energy transfer. So it's something I've been wanting to go and study for a long time. Now, the way we are treating vibrations, we are not limited by any kind of particular form or model spectral density. So what we have done here that I think is different from what has been done before in these systems, have been studied enormously to a great extent by through experiments as well as theory and simulation. And what I think we've done that's different is we're able to treat the precise vibrational parameters from the 50 normal world vibrations on each chlorophyll unit that have non-zero Huang-Rees factors. And we get those parameters from experiments, from spectroscopy. Here are the Huang-Rees factors, and this is what we're including these calculations, no more, no less. There is no additional environment or any kind of assumption about those parameters. So, all right, this is a busy slide. All right, so what we have here is a chain of chlorophyll units. We go from 2 to 19, as well as a ring. We can wrap it around and make a ring out of the chain. And we're trying to see what the energy transfer dynamics is like with and without vibrations. So let me start with a dimer. Here's a chlorophyll dimer. And in this case, if you include without vibrations, what you get is sinusoidal oscillations up and down. This is just a two-level system, right? I'm not drawing it here. But once you include vibrations, what you get is damping of the oscillations, but still you get oscillatory dynamics that persist. It goes on for a while. All right, that means we are in that weak intermediate coupling strength, and temperature is kind of intermediate here. In fact, there are a lot of parameters that are very similar. They fall in the same ballpark, and that's what makes things very interesting and complex. And now, here, we are looking at the pentamer. So now I have a chain of 5 chlorophylls, and without the vibrations, electronic dynamics looks like this. It makes a small recurrence and then makes a full recurrence and keeps doing this. You can study these structures from the eigenstates, pretty straightforward here for small chains. But once you add the vibrations, what happens is you get some smearing, of course. So you get the population of the initially excited state doesn't go down to 0 anymore. It makes its shoulder here, goes down, and then goes up. And the amplitude of the oscillation is diminished compared to what happens without vibrations from 1 to about 0.4. And here you can see on the right, you can see the excitation probability as a function for the various monomers as a function of time here. You can see for the here the pentamer, you get a wave pattern, this oscillation here, you can see the oscillation at this later time. But when we go to longer chains, what happens is even the electronic dynamics is very strongly damped. So here's a chain of 15 units, and here is the excitation, the probability, the survival probability of staying in the initially excited state. It only comes back a little bit. Of course, if I look at very long times, it does come back more than that. But here's what vibrations do, and that's something that we know in general, we have known for a long time. Vibrations, the effects of vibrations in environments and phonons and decoherence in general tend to be more and more drastic as you go to longer times. So what happens here is the vibrations, they smear out this oscillation and they smear out the next one even more and even more. And what you get here is, if you look at long time, which I'm not showing here because it's not published yet, what you get is small amplitude oscillations that persist, but they don't come back. They don't become large amplitude oscillations. You can see this wave pattern here on the right. So this is 300 degrees Kelvin. There are no artificial spectral densities or broadening factors or anything else here. And the only parameter in these calculations is the electronic coupling, which we got from electronic structural calculations. That's a single parameter. And if we have spanned a range of this electronic parameter to make sure that it doesn't really alter the results. So what we see is small amplitude persisting oscillations here, a little bit of coherence left over, which we think most likely would be wiped out if we were to embed this in a biological environment, which we plan to do. But for now, what we wanted is to have a very clean calculation where we are only including vibrations with experimental parameters and nothing else. There's nothing else here in the dynamics of this. So, all right, let me summarize. So what I'd say, listening to the other talks and everything, quantum dynamics has gone a long way. Quantum chemistry has gone a long way, definitely. And there's been so much progress in dynamics in recent years. And I would like to point out that path integral methods that have been for a long time look like they can't really do very much because it's such enormous complexity and you get the sign problem. In fact, they can do quite a lot for dynamics. They offer the path integral formulation offers some advantages. I think I already explained those, but you don't have wave functions. And in some cases, I would say the path integral offers the only avenue to fully quantum mechanical exact simulation without approximations in condensed phase dynamics. So, and also I would like to say that we are at a very exciting point because a number of problems that look like they were impossible before, now they're beginning to appear to be within reach of simulation. And I would like to thank my current and recent group members. I already mentioned their contributions, and I would like to thank all of you for your attention.
Thank you very much, Nancy. So the Q&A is open now. If something drops in, I will have time to post that. So first of all, I have a few questions, or at least one. I agree with Bill. This was very, very impressive. I see the big molecular systems you're treating, and I'm trying to figure out how to design a CAS-SF calculation for that, and realize, of course, that that's impossible. Could you tell us a bit about sort of the how you treat the electronic coordinates and the electronic parameters, because you really didn't talk anything about if it's DFT or if it's molecular mechanics, or what's behind the scene. And also in that perspective, the dynamics can never be better than the electron structure theory that is behind it. Or could you dwell a bit about this, please?
Absolutely. So as I said, this is in this case, this is a Frankel-Exton Hamiltonian. And there's basically one parameter here. They're all identical chlorophylls. So there's one parameter that is the coupling of the excited state of A to the ground state of B and so on. The excited, the 1, 0, 0, 1 coupling, right? So as I said, that is a single parameter. We obtained that from previous calculations. Shaul Mokamel has done calculations as well as others. But just in case that is not super accurate, it's a single parameter, and it's easy to examine the effects the single parameter has on the results. And we've done that, and we've confirmed that it does not really change the results we get in a qualitative way. We also have included static asymmetry, static disorder, asymmetry of the symmetry breaking of the chlorophyll dimers, the chlorophylls, some dimerization as they form those rings. And that's all we need to do in this case. We're not redoing the electronic structure. We are just using the Frankel-Exton Hamiltonian with a single parameter here. And as I said, the rest comes from vibrations from experiment.
Thank you very much. Another question I have is, Löwdin was one of the first one to suggest the possibility for quantum chemistry in biological phenomena, and that evolution itself sometime would drive molecular scaffolding to utilize quantum effects, like, for instance, the dephasing or phasing or quantum interference. Have you seen any cases where this would really be the case?
Well, I think that this is what we, if I understand your question, this is what we see here. So we get these oscillations are the result of electronic interference, and it's the interplay between the quantum electronic interference and the vibrations that determines the outcome of these populations. So all the interference, absolutely, there's a lot of interference in here in these systems.
So life itself is a manifestation of quantum effects.
Well, there are definitely huge quantum effects in biology, absolutely.
Thank you very much. So thanks again, an applause to you. So we're about to finish the third session of the first day. Again, I would like to thank the speakers we had today. Rod, Wolfgang and Pekka started out in the morning. Then for the second session, we had Francesco, Spiridola and Sharon. And now we've wrapped up with Bill and Nancy. 8 of the 16 presentations we're going to have. Tomorrow, we're going to start again at 12 o'clock Central European time, 12 o'clock sharp. And tomorrow we're going to listen to things that will answer the questions better than nothing, or I have no time for science as usual. And of course, my big favorite, quantum machine learning. So until then, until tomorrow, have a safe evening and see you then. Thank you for today.